Good day, everyone. Today, let us have another example or application of the uniform circular motion, which is we will analyze the simple harmonic conical pendulum. But before that, take note that in our previous video for the uniform circular motion, we learned that any particle that travels on a curve undergoes acceleration. And there were two components of acceleration while traveling along the curve. The tangential acceleration, which is due to the change in velocity magnitude, and also the change in velocity direction that results centripetal acceleration. Now, if the particle travels at a constant speed, meaning there's no change in velocity magnitude, hence the tangential acceleration is 0, then it follows that we have only the acceleration due to the change in velocity magnitude, and that is directed towards the radius. We call this as uniform circular motion, whose acceleration is only towards the radius of the circle because there's no change in magnitude. Now, according to Newton on the second law, that if there is an acceleration, there is always a centripetal force. Now, because the acceleration is centripetal acceleration, A sub c, then the force should be centripetal force, which is F sub c. And in that video, I will provide the link below. The relation of the centripetal acceleration is the square of velocity divided by the radius. Remember, the radius is r is the radius of the circle, and the square of that velocity divided by r is the centripetal acceleration. Now remember that the acceleration is directly proportional to the velocity but inversely proportional to the radius, and the acceleration does not depend on mass regardless of the mass. The acceleration is the square of its velocity divided by r. Hence, the force, if we multiply the mass of the moving particle and the acceleration, centripetal acceleration, the result is mv squared over r. And we can notice that the centripetal force depends on mass, directly proportional. And it is directly proportional also to the square of the velocity, but inversely proportional to r. These are the relations we obtain in that discussion. So any particle that travels around the curve undergoes acceleration. So therefore, there is always an unbalanced force while rotating along the curve. But remember, even if the velocity is constant, the centripetal is always present on that activity. So we call this as uniform circular motion because the velocity is constant. For non-constant velocity, we cannot say that it is a uniform circular motion. Okay, now let's have an example of the uniform circular motion, simple harmonic pendulum. Now, what is simple harmonic conical pendulum? Now consider a point, a fixed point, and we have the bob connected by means of string. One end is connected to the bob and the other end is connected to a fixed point. And the object should be a massive object. It should be a dense material. Okay, if we have a distance from the vertical, if we move it at a distance r, then allow that to rotate around the circle at a constant distance r, then the r can be considered as the radius of the pendulum. Then the angle is called as the amplitude angle, and the mass of the pendulum bob is m, and the length of the string or the cord is the length of the pendulum big letter L. So these are the quantities for the simple harmonic conical pendulum. So remember that we call it as a simple harmonic conical pendulum because the velocity is constant. Simple harmonic means the velocity is constant. There is so-called periodic activity, meaning the time is constant, traveling at one complete revolution of the particle. Conical, because in that configuration, the particle moves at a circle, then it forms like a cone. No? Okay, so then what is the if you have this one, so therefore this object will rotate around the circle at a constant speed, meaning r is constant and the length is constant, and also the angle and the velocity is constant. So we call this a simple harmonic conical pendulum. Now our task of this activity, our objective is to provide a relations of the period of the pendulum big letter T to the given parameters. The given parameters are, we have the angle of amplitude, we have the length of the pendulum L, and we have the mass. So given only these three, what is the period? Calculate the period as a function of that parameters, and we will also calculate or give the relation of the constant velocity as a function of L and theta. So what are the relations that involves on these parameters? Aside from that, we will also provide a mathematical relation of the tension in the cord as a function of the mass, the angle of, or the amplitude angle. So those are the three objectives that we need to provide in this video. Okay, so then remember that when you look at the figure, the vertical line from the fixed point R is always 90 degrees, which means that at any point along the curve, it forms a right triangle. Now take note that we don't know what is R, because the only given is the angle of amplitude angle, the length, and the mass. But take note, because it is a right triangle, then we can solve for R in terms of L and theta, because R is opposite to the angle theta. So L can be considered as the hypotenuse. So meaning if I take sine theta, it is R over L. Now, diagonal product, then L can be computed, or R can be computed using L multiplied by sine theta. So therefore, we can always calculate R, because we have theta and we have L, vice versa. Okay. Now, take note that there are forces acting on the object whose mass is m. Now, what is the tension in the cord? Now, meaning, what is the tension in the cord? Because aside from the weight, we have the tension, no? There are only two forces, the weight and the tension in the cord. Okay? But take note that the velocity, no? If we are trying to solve for the velocity while rotating along the curve, remember that velocity in kinematics, it is the displacement over time. And the displacement of the mass m is the circumference of the circle, which happens to be 2 pi r. If you divide that by the time is period. We call it a period because it starts from there and it ends at the same point. So we call it as a period of the pendulum, one complete revolution, and the time is period. So the 2 pi r divided t is the velocity, which means that the velocity can be computed if we have r and we have t. But r, remember, is L over cosine theta. So substituting L sine theta. So meaning substituting, we have 2 pi L sine theta over t is the velocity of the pendulum. Okay? So if we solve for t therefore can be calculated vice versa by 2 pi L sine theta over the velocity, transforming the upper equation. Okay, so therefore we will preserve that formula. So for now, we can solve only period, no? If we have the angle, if we have the length, and we have the velocity, but we don't know the velocity yet. Okay, so therefore we will find first the velocity in order to obtain the period of the pendulum. Okay, now again, the particle m, while rotating around the circle, it has two forces, the weight and the Okay, we have the weight and the tension in the cord. But remember that while rotating around the cord, we have the centripetal force or acceleration towards the center of the circle. And also, it has the centripetal force because according to Newton, there is acceleration, there's always centripetal force, a force also. Okay, so if we overlay that to the Cartesian plane, x should be along the center. Why? Because we know that the unbalanced force of that particle is towards the radius. There's no unbalanced force along y, remember, because it won't move down, it won't move up if the angle is constant. Remember, while rotating, we have the maintaining angle, and that because it's amplitude angle, and L is also fixed, hence R is constant along the travel. So therefore, there's no unbalanced force along y, and the unbalanced force is along x-axis because it is where the centripetal acceleration directed, and hence the force is also towards that direction. Okay, but remember that acceleration is not due to the magnitude of velocity, it is due to the change in velocity magnitude. So if the velocities keep on changing, then there must be an acceleration towards the center. So therefore, we are now ready to provide the free body diagram. No? So there are only two forces. We have the weight downward, it should be negative y, and we have the TC, which is along xy plane. It is not directed along x, it is not directed along y. So it has two components. So therefore, we can provide the tension in the cord in terms of weight. Why? Because take note that when you look at the free body diagram, the component of TC parallel to y should be equal to W, for the reason that it won't change along y. And the component of TC along x is the centripetal force. So therefore, the tension in the cord plays an important role to solve this problem. The component of x is the centripetal force, and the component of y of tension in the cord is actually equivalent to the weight of the metal. That's why the reason why the weight of the pendulum bob will not move down. Why? Because there is a component of the tension which tends to move upward. Okay, and take note that the angle from y towards the tension in the cord is theta. Okay, because remember in geometry, two parallel lines cut by transverse line. The transverse line now is the line of the string. Then the angle, alternate angle must be the same. Okay, so with that, we can sum up all forces along y and equate that to 0. Why 0? Because the net external force along y should be 0. As I've said, it won't move up, won't move down, so the sum should be 0. So it is called as the equilibrium principle. Balance, force are balanced. The weight was balanced by the component of TC. So summing up all forces along along y. What are the forces along y? We have the component of C, TC along y, positive. So it should be cosine because the angle is adjacent. Then minus the weight. So it should be cosine TC cosine theta minus W. Okay? But take note that W is what? W is mg. So solving for TC, it should be mg over cosine. So transpose W, the W is mg, divide both sides by cosine, then TC is mg cosine of theta. So this is the relation that can calculate the tension in the cord. So the requirement, if you are asked what is the tension in the cord, if given theta, L, and the mass, then it should be mg over cosine theta, which means that TC does not depend on L. Even if how large is that or how short is the length of the pendulum, then the TC only depends on its mass and its angle, theta. Okay, so mg cosine theta, which is equal to the tension in the chord. So we will preserve that formula. Okay, so far we have the relation of the period, which is 2 pi L sine theta over V, but we don't know V. Now we have Tc. Tc means the tension in the chord. Please do not confuse, because Tc is a force, while T, big letter T, is a period. It is a time. So be careful, no? Tc is tension, so the unit should be Newton, while T, big letter T with the subscript, it has a second, time of second, unit of second. Okay, then we are done in summing up all forces along y. We know that the forces along y is 0. Now proceed to the x. Summing up all forces x, take note, is not equal to 0, because the object is moving. But the force is directed towards the radius, means it is the centripetal force. So if we sum up all forces, okay, from the free body diagram, sum up all forces along x, we have only one force, and that is what? The component of Tc along x, and it should be sine, because y is adjacent, then the x component should be opposite. So it should be sine theta multiplied by Tc. Okay, but as I've said, if you sum up all forces along x, it is also the same as the centripetal force, which means that we can replace the summation of forces along x be equal to Fc. And Tc, remember, is what? We have already calculated the Tc, and it is mg over cosine. So replacing Tc with mg cosine over cosine theta, and replacing the summation of force along x by the centripetal force, this will be the result. So Fc for the summation of force along x, then the Tc is mg over cosine theta multiplied by sine theta. Now, using our derived formula for the uniform circular motion, remember Fc is what? mv square over r in the previous slide. Okay, so Fc becomes mv square over r is equal to mg cosine theta multiplied by sine theta. Okay, so take note that r is not given, but r is L sine theta in our previous slide again. So replace r with L sine theta, so we come up with this: mv square over L sine theta is equivalent to mg over cosine theta multiplied by sine theta, which means that we can cancel the mass, so mass can be eliminated. Then the sine becomes sine square if you take diagonal product. So solving for v, then take diagonal product of that, then take square root, then v square now becomes what? The v square, or the v, is equal to square root of gl sine square theta over cosine theta. Remember, m was eliminated. Okay, so let us continue. Now analyze that in algebra. If we take cosine, or if we take square root of sine square of theta, the answer is sine theta. So this will be reduced, simplified into the form of sine theta multiplied square root of gl over cosine theta. This is the formula for the velocity. Now notice that we can solve now the velocity because theta is given, and given also the length of the pendulum, and the g is the 9.81, which is the Earth's gravitational acceleration. Okay, so we can solve for the velocity, and this is the relation of the velocity as a function of L and theta. We can always calculate. Now, this velocity will be substituted to our previous derived equation, so replacing that velocity in order to provide the tension, or the period of the pendulum, t, not tension. So replace the v with sine theta multiplied by square root of gl over cosine theta. Then take note that we can cancel. Look at the result, possible result. Sine theta will be cancelled out. Then combine the like terms, meaning if you fuse the L, okay, then the result becomes what? The result becomes 2 pi square root of L cosine theta over So use your algebra power. Okay, so let us continue again. So again, for now, we can now solve. This is now the period of the pendulum. So meaning, the period of the pendulum can be calculated only if we have the angle, amplitude angle, and the length of the pendulum. So 2 pi square root of L cosine theta over the Earth's gravitational acceleration. Okay, now, if we consider a very, very small angle, remember the amplitude angle is the angle from the vertical towards the length of the pendulum. No, if that angle is a very small, meaning if it is more or less 10 degrees, no? Between 0 to 10 degrees of the amplitude angle, the cosine of that angle is approximately equal to 1, which means that if your simple harmonic conical pendulum has an angle between 0 to 10 degrees, a very, very small, then the cosine of that angle is 1, which means that the above equation becomes simplified to 2 pi t, which is the period of the pendulum, is equal to 2 pi square root of L over Z. Now, why we do this? No? Now, this formula is very important. No? Remember that the period is only a function of L. Meaning, if you have L, you can always solve for theta, provided that the angle is a very small angle, amplitude angle. Meaning, if you have the period, if you can provide a period and you have the L, then you can compute for Z. So this is actually a strategy on how to obtain the Earth's gravitational acceleration, because you can calculate the Z if you have the period and you have L, and that will be our next video, performing an experiment and providing the Earth's gravitational acceleration location specific. Remember that the acceleration is, we use the 9.81 as for calculation purposes, but remember that the acceleration is location specific. It might have different values, but on the average, it is approximately 9.81. That we use only 9.81 for calculation. Okay, so that will be the next. Now let's continue. So therefore, let us have the summary of the activity. Meaning, if we are given problem in a simple harmonic pendulum, given only the angle, amplitude angle, given the L, and given the mass without R, we can solve the velocity, we can solve for the period, okay, we can solve for the tension. So that the tension in the cord, which is the force on the string or the cord or the rope, is mg over cosine theta. So meaning, if you have the mass and you have the angle, even without L, then you can solve always the tension by just using the angle and the mass. Okay, the greater the mass, the greater the tension. Take note of that. Now for the period, it is 2 pi L sine theta over V. But remember, we don't know velocity. But the velocity is what? Sine theta multiplied by square root of GL over cosine theta, which means that the velocity can be computed because we have already the angle and we have the length of the pendulum. So combining these two, the result is 2 pi L cosine theta over Z. Okay? And for a very, very small, then we have T is equal to 2 pi square root of L over Z. So these two can be calculated. You can use only the 2 pi square root of L over Z if the angle is very small. But in general, we have 2 pi square root of L cosine theta over Z. So these are the important relations. If you are solving now problems in oscillations and the problem is conical pendulum, then these are the available formulas for you to use. Okay, no need to derive, and we can use this one. But remember that very important that you can derive the formula. Okay, so let's have the sample problem. Now remember that the formulas are already outlined. No, that formulas are ready to use. Now suppose given the amplitude angle of 30 degrees, and we have the length of the pendulum as 1.5 meter, and mass is 5 kilograms. The question is, okay, calculate the following: the tension in the string or rope or cord, means TC. Then number 2, find the velocity of the pendulum bob, meaning the velocity, constant velocity while rotating around the circle. And lastly, calculate the period of the pendulum. Remember, there are 2 formulas for that. But take note that the angle is 30, meaning we cannot use the 2 pi square root of L over G because the angle is more than 10 degrees. So, to provide the solution is to use, number 1, you can use the TC is equal to mg cosine theta. So, for our solution, substitute that 5 kilograms by the 9.81 meter per second squared over cosine 30. Use your calculator, the answer is 56.64 newtons. So, we provided the quick answer of the tension because we have already the formula. This is the answer for number 1. Okay, for number 2. For number 2, you can use because you are asked to find the velocity of the bob. So use the formula. The formula is sine theta multiplied by sine theta multiplied by square root of GL over cosine theta. Then substitute the values. The theta is 30 degrees. The G is 9.81 meter per second squared. The length L is 1.5 meter. And the cosine of theta, which is 30 degrees. So simplify, use the calculator. The answer is 2.06 meter per second because it is a velocity. Okay, so lastly, for the period of the pendulum, we can use the 2 pi again, square root L cosine theta over G because the angle is 30 degrees. It is more than 10 degrees. So substitute the values. 2 pi square root of 1.5 meter multiplied by cosine theta, which is 30, divide 9.81 meter per second squared, and the answer is 2.26 seconds. This is the period of the pendulum. Okay, so these are the answers to the problem. Okay, so that's all. All you need to do is to keep on solving in order to exercise or expose some problems. You might be asked, for example, given the velocity and given the period, calculate or given the velocity, given the mass, calculate the period. So it depends upon the problem. So that's all. So see you. The next video is performing experiment on how to compute the Earth's gravitational acceleration. So thank you.